calendar. So after my talk for the opening, we will have the welcome first, or later. Okay, we will have the tutorial, and then the coffee break, and then we will have an official opening and welcome. So then with that, because we are also behind the time, I would like to invite Professor Fabio Cuzzolin for the tutorial on second order uncertainty, please.
Do we need to start recording from here? You do it from your laptop, Cadence? Okay. This is pretty heavy, so I'll try and make it through the talk. Right, so welcome everybody. I'm Fabio Cuzzolin, a professor of AI at Oxford Brookes University, which is one of the partners in the Epistemic AI Horizon project that funds this event. We can't do this because I need two hands to operate the keys, but we'll see, right? So we thought it was a good idea to give a first introductory tutorial on epistemic uncertainty for people who are not particularly familiar with the concept. And I hope to cover everything that is in here, but I might not do. So at the end, I'll just probably go through the last few slides a bit quick. But uncertainty is the fundamental concept under the Epistemic AI project. So I think we want to give at least a little bit of an introduction to what we mean by epistemic uncertainty and how it can be represented mathematically. And there isn't much about AI, so it's just purely about the mathematics of uncertainty, this tutorial. But I think there will be space and time in the open discussions later in the day to discuss, how this can be applied to artificial intelligence and machine learning. So what is epistemic uncertainty? There's two different types of uncertainty, although this is often neglected. This was recognized in fields like philosophy and business and economics. In economics, they call it predictable and unpredictable variations. We prefer the term second order epistemic uncertainty to describe what's called unpredictable variation. So second order uncertainty is about being uncertain about our very models of uncertainty. For instance, if your data is generated by a probability distribution, but you don't know what the probability distribution is, you have second order uncertainty, and this can be described in several different mathematical ways. There is strong evidence from psychology that second order uncertainty exists, and as consequences of human behavior, people are particularly averse to unpredictable variation. So they prefer, for instance, to bet on lotteries for which the chances are fixed and known, than to bet on lotteries for which they are uncertain what the probabilities are, even though the average outcome is the same. This is the so-called Ellsberg's paradox. So how good is the first part of the tutorial is about how good is Kolmogorov's measured theoretical probability, so classical probability theory, at describing second order uncertainty, and also the two main interpretations of probability theory, so the Bayesian and the frequentist. So as you probably all know, at least I hope so, the mainstream mathematical theory of uncertainty, at least first order uncertainty, is measured theoretical probability, developed mostly by Russian mathematician Andrei Kolmogorov. And it's an application of measure theory, which is the theory of assigning numbers to sets. This is measure theory. So measure theory is about mappings from numbers, from sets to numbers. But classical probability is about a very specific class of such measures, so additive probability measures, that assign a probability value to every subset of a collection of possible outcomes, or sample space, as you want to call it. And these subsets are normally called events. I trust you're familiar with this kind of terminology. So far it's just standard stuff. This is the definition of probability measure. It's a real value function on a probability space that is countably additive. some technicalities, but basically there's a probability space, which is your sample space or universe. There's a sigma algebra of events F, and then there's a probability measure E on the sigma algebra. So not all the subsets of your sample space necessarily belong to the sigma algebra, so they're not assigned a probability value. They satisfy three axioms. So the measure of probability of the empty set is 0, probability of the sample space is 1, probability is always in the interval 0, 1, but the main one is this additivity. So for all countable collection of pairwise disjoint events, the probability of the union is the sum of the probability of the event. Again, these have to be pairwise disjoint, which is a very, very strong assumption. People don't realize that very often, but where is this coming from? And does this make sense when one wants to model epistemic uncertainty? On top of that, probability, this is mathematical probability, but then probabilities are different interpretations. And the two main ones are the frequentist and approach and the Bayesian approach to probability. Frequentist is more objective and the Bayesian is more subjective in nature. Frequentist inference is, in frequentist interpretation, the probability of an event, it's a relative frequency in time. So you measure the outcomes of random experiments, like loads of times, and you count the relative frequency by which the events happen, and then you say these are the probabilities. I mean, I'm not being entirely correct now in my terminology, but more or less this is what they mean by probability. Was developed by Fisher, Pearman, and Niemann, mainly in the 1930s, I think. And there are three main tools in frequentist probability, and the main one really is statistical hypothesis testing, but there are others like confidence interval analysis and so on. What happens in statistical hypothesis testing is that it's a very specific and narrow setting. So you state what your research hypothesis is. I don't know, could be like, usually this is used in medicine, so it could be like about this person has this type of disease or then that type of disease. You state the relevant null and alternative hypothesis, so the person doesn't have that disease. You state the statistical assumption being made about the sample. So for instance, the sample is statistically independent or the distribution of the samples. Then you compute a number of relevant test statistics, I don't know, means and variances and other sort of. A statistic is just any measurement you extract from a sample. That's a statistic. You derive distribution of this test statistic under the null hypothesis. You set a certain acceptable significance level to you, so a probability threshold below which the null hypothesis is rejected. Then you compute from the observation the observed value of the test statistics, and then finally compute the p-value, so the probability under the null hypothesis that of something and test statistic at least as extreme as the observed value. And then you accept or reject the null hypothesis based on whether the p-value is above or below the threshold. So this is a diagrammatic interpretation of p-values. So this is your assumed distribution of samples, and this is your, say you set like a threshold of 0.05, and the p-value is basically the area under this part of the curve. So it is not, to be clear, it's not the probability that the null hypothesis is true or the probability that the alternative hypothesis is false, because frequentist statistics doesn't attach probabilities to hypothesis. But the setting is very, very limited. So it's just about testing whether the hypothesis is true or not, or it can be or not rejected, actually, I should say. And it is based on a lot of assumptions. You need to assume the statistical distribution of the data. You need to assume this. You need to assume that. And on top of that, I'll say more about that later. Another classical tool is maximum likelihood estimation, which was popularized by Ronald Fisher in the 1920s. It's based on a likelihood principle. So all the evidence in a sample relevant to a model parameter is contained in something called the likelihood function, which is basically a function of the sample data and the parameter. And then if you have a likelihood function, you can compute the maximum likelihood estimation estimated for the parameters by doing the argmax of this likelihood function. And again, you need to assume a parametric model, which is the distribution of the data given the parameters. This method has good properties in the sense it's one of them is consistency. There's a sequence of MLEs converging probability for a sufficiently large number of observations to the actual value being estimated. The other main interpretation of probability is subjective probability. Some terminology. So by epistemic probability, we philosophers mean the degrees of belief that an individual assigns to events based on their knowledge of the state of the world. So in the frequentist interpretation, probabilities are basically relative frequencies of things that happen in the real world, whereas in the subjective interpretation, probabilities are attached to events by individuals. So there's a huge philosophical difference between the two types of interpretations of probability. The subjective probability branch is mainly due to Ramsey and Definiti. Definiti was an Italian mathematician from the early 20th century, like 1920s, I think it is, most important, 1930s. Bayesian inference is the mathematical incarnation of the subjective probability approach. And there is, I think, if you guys are in computer science or AI, you will know all these things. So computer scientists are much more familiar with Bayesian reasoning than the frequentist interpretation, I suppose, whereas in other fields like biology and medicine and business, the frequentist approach is still dominant. When you validate a drug for approval in a country, this usually they run statistical hypothesis testing. They don't do Bayesian reasoning. So in Bayesian reasoning, a prior distribution of the parameters before any data is observed might depend on hyperparameters, but might not. You have a likelihood, which is the distribution of the observed data condition on the parameters. And then you have a posterior, which is obtained by Bayes' rules using the formula that I think everybody is familiar with. What are the main problems with the probability, mathematical probability in the Kolmogorov definition and its two interpretation? So this is why I call this section beyond probability. So is anything wrong with these things? I mean, there are lots of things, from my point of view, at least, there are lots of things that are wrong. I think I'm keeping up with time. So on the one hand, measured theoretical mathematical probability is not general enough because it cannot model properly missing data or propositional data or unusual data or ignorance. So there's a bunch of problems with additive probabilities from a technical point of view. The frequentist approach cannot really model pure data without designing an experiment, so assuming that you know the probability distribution of the samples beforehand, and the only thing that is unknown is the parameter value. In a way, you cannot even model properly continuous data because the notion of p-value, the fact that you're taking the integral of the probability over a certain threshold is because in measured theoretical probability, the probability of any given point of the continuous space is zero. So in a way, it's not even a proper way of mathematical probability cannot really model continuous data in, there's a bunch of people that made their career about studying zero probability events and blah, blah, blah. And also it models scarce data only asymptotically. So it has good asymptotical properties, but that has little use to computer scientists or people in AI. They actually have to work with whatever data they have. Bayesian reasoning also has several limitations. It cannot model data like ignorance, pure ignorance, and I'm going to argue about that. It cannot really model uncertain data, so data that is imprecise in nature or fuzzy or uncertain. Cannot model pure data without assuming a prior. You need a prior, even when you don't have a prior, and you cannot properly model scarce data, but again, only asymptotically. And I'll say how. So hypothesis testing, so the feature, the probabilistic interpretation, but like I said, the scope is very narrow. It's about just rejecting or not rejecting a hypothesis, although it can provide confidence intervals, to be fair. The criterion is very arbitrary. Who decides what an extreme realization is? So how do you choose the alpha? What is the deal with these numbers, 0.05, 0.01, that appear all the time? And the whole tail idea comes from the fact that under measure theory, the conditional probability or p-value of a point outcome is 0. So basically, they put a patch on the underlying problem with mathematical probability by saying, okay, I'm going to compute this integral instead of because the null hypothesis is really about the pointwise value. It's not about the upper interval. So, they're just patching a problem with mathematical probability. It cannot cope with pure data without assumption on the process or the experiments that generated them. And, yeah, the Bayesians do that too, but, from a point of view of respecting the data, this is very undesirable. And finally, it can only deal with scarce data asymptotically, like the MLE properties of consistency at infinity. Bayes also has problems. It's pretty bad to represent the ignorance because, yes, you can use uninformative priors, but, these are just not adequate because they produce different results on different parameterizations of the sample space. And there are simple experiments that show that, actually. Also, Bayes' rule assumes that new evidence comes in the form of certainty. So the new evidence only comes in the form event A is true, and then you can condition on that event. Whereas in the real world, this is often not the case. You have all sorts of different types of evidence. But I think the biggest problem is the prior, and beware the prior. So you need a prior, and in my view, this results from a fundamental confusion between the original subjective interpretation and an objectivist view of Bayesian reasoning as a rigorous procedure. So initially, it was thought of as a model of human thinking. People have priors, then they look at evidence, and then they revise their beliefs based on. But algorithms don't have priors. Machines don't have priors. They don't have any prior life. So you have to impose a prior, and then you have to design it, and you think about it, and what should I use? And 99.9% of people end up using always the same priors because it's just easier, and people are lazy, and there is no good reason to select one prior. And then, yes, there are patches in Bayesian reason, like empirical Bayes and ways of, going around the problem, but really fundamentally Bayesian reasoning is subjective, a probability interpretation, not an objective procedure for reasoning with data in the real world. Why should we pick a prior? Either there's prior knowledge or there isn't. So, but the formalism doesn't allow you to work without priors, at least in its vanilla form. Also, yes, all will be fine in the end because asymptotically the choice of the prior doesn't matter thanks to this Bernstein for Mises theorem. But we're not at this. We are never at infinity. So you're driving an autonomous vehicle. It never has infinite amount of data available to it. So yeah, asymptotic results are very nice, but they're little used for practitioners or people who actually need to use the data. Okay, so all this is to say that there are other ways of measuring and modeling uncertainty mathematically, and I think most people are not familiar with these alternative methods, which is the topic of this talk. I'm starting from a simple example here, which is just a die. You have a die. Die is a discrete random variable. And anybody not familiar with random variables? Anybody who has not heard of random variables before? Good. Nobody. Good. So a die is a discrete random variable. So it's a mapping from the finite sample space to the real line, which is measurable. There's a probability space, phase 1, phase 2, phase 6, with maps to real numbers 1, 2, 3, 6. There's no need for measurability in the final case, but there is one in the continuous case. Now, imagine that, two of the phases, like phase 1 and phase 2, are cloaked, and you still roll the die. what is it that you get mathematically? You get set values observation because you get the 4 normal faces, and then you get the cloaked face, assuming that you don't see what's on the sides. The cloaked face outcome it means only that the face is either phase 1 or phase 2, but you don't know which one. So you have the same probability space, but the mapping now is different. So you have mappings from the phases 3 to 6 to the real numbers 3 to 6. But phases 1 and 2, they map to the set 1, 2. So you observe set valued outcomes instead of individual outcomes. This is a set value random variable where the mapping is from the probability space to sets of the real line, and all random sets. So random set and set value random variable is the same thing. Basically, these were defined almost independently by a bunch of people, Matron and Kendall, Nguyen, Molchanov, more recently in the last 20 years, wrote a couple of nice books on material random sets. So this is to argue that whenever data are missing, observations are intrinsically set valued. You can think of the observation as being intrinsically set. So to do an example, suppose there is a murder and there are 3 people on the trial for Peter, John, and Mary. So your hypothesis space is composed by these 3 people, Peter, John, and Mary, and there is a witness testifies as the person they saw was a man. This amounts to supporting the proposition that A equal to Peter, John. Should we take the testimony at face value, or if you test, the witness was tested, machine reported an 80% chance that it was drunk. So we should also partly support the so-called vacuous hypothesis. Either Peter, John, and Mary can be the murderer. So you can assign under this model 80% chance to proposition A, Peter, John, and 20% chance to proposition theta, so Peter, John, Mary, the entire space. So, but even when, so this is a kind of propositional sort of evidence. So sometimes evidence supports propositions instead of points of a space. But in Kolmogorov measure theoretical probability, you have to satisfy support for individual outcomes, even when the available evidence is really in support of sets. Which is unreasonable. It's an artificial constraint due to a mathematical model that is just not general enough. So you have no elements to assign this 80% probability to either Peter or John, because the only evidence that the culprit is male, but you don't know who he is. And the problem for this artificial, the reason for this artificial constraint is the additivity axiom or probability measure. So, but fortunately, this is not the most general type of measures for sets. There are actually a minimal requirement called monotonicity that can potentially be suitable to describe probabilities on events. And if you replace the additivity axiom with monotonicity, which is, I think, I don't have a slide on that, that the measure of A is smaller, is not greater than the measure of B. If A is contained in B, this is monotonicity, you get an object called capacity, monotone capacity. Random sets happen to be capacities in which the numbers assigned to subsets are given by a probability. So as capacities, so random sets can assign mass directly to propositions. So they support they provide an easy way of encoding propositional evidence. In machine learning, which is I think the topic of today's meeting, also is the topic of the project, you always have to generalize from scarce data. So you design algorithms that learn from data, but you train them on a ridiculously small amount of data. So how do you make sure that the models you learn are robust to new situations? I counted before, problem implementation. Yes, so there is a part of machine learning called statistical learning theory, mostly due to Vapnik, that is based on traditional probability theory that is designed to deal with that kind of stuff. So produces generation bound on the future performance of models based on trained data, but everybody knows that these bounds are useless and nobody uses them in practice. So how do you deal with scarce data? So there's somewhat naive objection to probability distributions assume an infinite amount of evidence. So in reality, finite evidence can only provide a constraint on true probability values. This is very intuitive, but it's not entirely correct because, or relevant, because those who believe probabilities to be limits of relative frequencies, the frequentists, never really estimate the probability from the data. They, at least not under the hypothesis testing scenario, they just assume or design probability distribution for their p-values. So Fisher says, fine, I can never compute probabilities, but I can still use the data to test my hypothesis. In opposition, those who do estimate probability distribution from the data, like the Bayesians, do not think of probabilities as infinite accumulations, or at least they shouldn't. Because the probabilities in the Bayesian framework are subjective degrees of belief. They're not limits of relative frequencies. And in my experience as a computer scientist, a lot of practitioners in computer science, they mix up the two all the time. So they confuse the frequency interpretation with Bayesian reasoning, and they mix them up in their papers and like a mess. But, you know, these are really two radically different interpretations of probability. So Bayes says, I only need to be able to model a likelihood function for data to do MLE. I don't need to estimate my probabilities for all events. In practice, really, frequentists do estimate probabilities from scarce data when they do things like stochastic regression, like logistic regression, and the like. So this objection holds to some extent. And the main problem with both approaches is asymptotic evidence, which I try to represent with this picture. Don't know if it's effective or not. You know, there's a light at the end of the tunnel, but the tunnel is infinitely long. So, you know, that's nice for mathematicians, but it's very little comfort for practitioners. Computer scientists have to deal with finite amounts of data. Yeah, so we have limit properties or MLE estimates, and we have the for frequentists, and we have the percent for Mises theorem for the Bayesians. But you know, who cares what happens at infinity? Not a machine learning model. What happens here and now? What about smart cars or any other application of machine learning? The biggest problem I personally have with Bayesian reasoning is the modeling of pure data, because Bayesian reasoning requires modeling data and the prior. And actually, if you want to be picky, you also need to select the proper hypothesis space. So you have three different choices. That you select the parameter space, you select the prior, and you select the likelihood. So prior is just a name. I mean, if you think about it, you know, as a model of human reasoning, prior is just a name for beliefs that are built by people over a very long period of time from the evidence that you observe. So longer time has passed that all track record of the observation is lost, and all is left is just the probability distribution. It's a bit like learning a model. You know, some approaches in machine learning, you learn a model from a bunch of data, then you discard the data, you just keep the model, and you have the weights of your network, but you don't remember what the data that generated that model. And the prior is just the same. So it's a probability distribution that it's learned from a lot of observations over time. Then humans have limited brain capacity, so they forget about everything most of what they've seen and heard, and they just retain this prior in their hand. You know? So why should you pick a prior? It makes sense. I mean, as a model of human thinking, it makes sense. But do you need to pick a prior? Either there's prior knowledge or there isn't prior knowledge. But in Bayesian reasoning, you need to pick one because the mathematical formalism requires it. And in my mind, this is a result of a confusion between the original subjective interpretation and the objectivist view of rigorous objective procedure. Then Bayesians, yeah, they go on damage limitation law, they pick the least damaging prior, like uninformative priors, they do empirical based, you know. There is a fundamental problem with the setting. All would be fine in the end, yes, we have these results, but who cares what happens asymptotically? Why is picking the right prior or the least damaging prior very difficult? Because prior distribution is typically hard to determine, and then you go for something like Jeffrey's prior, which is the Gramian or the Fisher information matrix. But this violates the strong likelihood principle because inferences depend not just on the data likelihood, but also on the universe of the possible outcomes, so the parameterization, basically. Uniform priors on top of that can lead to different results on different parameter spaces with the same, using the same likelihood, which is pretty funny, you know, but hypothesis testing is the same. So if you choose two different hypothesized distribution from your observation, you might get different outcomes, like reject or not reject the same hypothesis using the same data. So the design choices in both of these formalisms are so strong that the data becomes marginal. So this is a quote from this guy, Edwards. It's sometimes said in defense of the Bayesian concept that the choice of prior distribution is unimportant in practice because it hardly influences the posterior distribution at all when there are moderate amounts of data. By moderate, they really mean infinite amounts of data. The less said about this defense, the better. So, it's just not holding up. What about the frequentist? The frequentist approach is intrinsically unable to describe pure data without making additional assumption on the data generating process. But in nature, and as a computer scientist, you don't design experiments, you just get data. The data comes your way, right? And you have to deal with it. There are no stopping rules and the experiment never ends. So, so you can think of these people that came up with the frequentist approach, they're like this old scientist, a 19th century scientist, sits in his lab and does his own little experiment to analyze, which means break up a specific aspect of the world in their lab. And then you can run your experiment, you have full control of your experiment, but in machine learning, in AI, you don't have full control of anything. And like I said, in both cases, the same data can lead to opposite conclusions. So you can have different experiments can lead to the same data, whereas the parametric model employs, or the family of probability distribution that you assume is linked to a specific experiment. But frequentists don't have a problem with this. When you talk to them, they say, yeah, we know this happens, but we're fine with that. But I'm not particularly fine with this, having different results with the same data just based on different assumptions, to be honest. That can be said of most of science. I mean, it's fair to say, but at least this should be recognized. This is a weak spot. So the Bayesian reasoning is pretty bad at dealing with ignorance because uniformity priors, like I said, can be pretty dangerous. There are papers by Andrew Gellman and others about this. They violate the strong likelihood principle. They may be anormalized. The wrong priors can kill a Bayesian model before infinity. And priors in general cannot handle multiple hypothesis spaces in a coherent way. This is described in Glenn Shaper's terminology as a family of frames, or family of sample space. But the good thing is, reasoning with random sets, in particular the finite incarnation core belief functions, doesn't require any prior. And they can actually represent ignorance using the vacuous function that assigns the whole probability one to the entire hypothesis space. So by extending your mathematical framework from additive probabilities to capacities or random sets, you can deal much more naturally with all these sort of problems, which I'm going to show next. Another interesting point, like I said, I don't think I'm going to be able to cover all the material in this slide, but I hope this will give you at least a flavor of, what the problem is and what are different ways of modeling this. Rare events is I found it a very interesting problem. How do you predict rare events? It's very challenging. You can figure the dinosaurs, before they died, were probably worrying about overpopulation. The earth was full with dinosaurs, right? And filled with dinosaurs. And in the end, all of a sudden they were gone. And maybe we're doing the same. My point is that predicting rare events is very, very challenging. Rare events are events that span regions of the hypothesis space or the sample space that are very seldom, if any sample at all. So it's an issue not just with the quantity of the data, but with the quality of the sample. And this is a problem that we have in AI too, because when you train a model on training set, your training set never spans the entirety of the possible space of observation. So that causes the bias that we all know about. So how do you deal with rare events with the probability? If your probability distributions for system behavior are built in normal times, I don't know, you have a nuclear power plant, it's working just fine. You keep collecting data points in the safe region of operation, then you build your logistic regression like this. You can see it's been shown, for instance, in this paper that this logistic regression function will systematically underestimate the probability of rare events at the tail of, far away from the safe region of operation. You can propose corrections for this, but really this is really an issue with the reliability of the model. So you should be able to model how uncertain this logistic regression distribution is based on the data that you have. So belief functions and other models for epistemic uncertainty can model second-order uncertainty. So rare events are a form of lack of information in certain regions of the sample space, and that arguably induces second-order uncertainty what the shape of the logistic distribution of what your probability model is. I'm going to skip this one because I want to move on to the next slide. So there's a bunch of reasons why mathematical probability with the Bayesian interpretation, the frequency interpretation are all inadequate to model epistemic uncertainty arising from real data. And also evidence doesn't often come in the form of that is required, say, by Bayesian reasoning. It can come in the form of propositional data, uncertain data. I didn't talk about it in those slides. I have an extended version which I also cover all these other topics. So in the second half of the tutorial, I'm going to tell you a little bit about particular theory, which is the belief functions theory, the one I did my PhD on, and then I'll cover lots of other approaches to mathematical epistemic uncertainty. Hopefully, not in a lot of detail, but at least you will come out of this knowing that there are such things. So what is Glenn Schaefer in 1976 wrote a book called The Mathematical Theory of Uncertainty of Evidence, which is the basis for the theory of belief functions. Where are these names coming from, like belief functions, evidence, and so on? So they're due to the fact that this is the theory of epistemic probability. So it's about probabilities as a mathematical representation of knowledge. So epistemic means knowledge, in Greek. So by epistemic probability, epistemic uncertainty, we mean uncertainty. So it's about our representation of the world. It's not the world in itself we are trying to model, but our representation of the world. And it's also a theory of evidential probability. So probabilities representing knowledge are induced by evidence. So evidence is out there in the real world. This is mapped to a certain representation inside the mind of an individual or a machine, and this is the epistemic representation of the world happens in here. In probabilistic logic, there are statements such as hypothesis H is probably true, which means that the empirical evidence available supports H to a high degree. So this is what we call the epistemic probability of H given E. And the rationale is that there exists evidence in the form of probabilities which supports degrees of belief on a certain matter. So this formalism is based on the idea that there is evidence out there, and this can be probabilistic in nature. And this evidence induces degrees of belief, epistemic degrees of belief, which are not probabilistic in nature. So they're more general than probabilities. And in particular, they're a form of random sets, the ones I illustrated with a random cloak die example. So this is kind of a representation that expresses that. You can see this is a random set because it's a mapping from probability space to a power set. So every point of the probability space is mapped to a set of your domain of interest theta. Art Dempster, who is the person that devised this first, called them multi-valued mappings, but these are really random sets. So you have basically the framework is such that you have probability evidence in the form of probability distribution in a certain space, like your witness can be drunk or not drunk with probability 20% or 80%. But this has implications on who the murderer is for your trial, right? So this implication is represented as a random set. So if the witness was not drunk, then the murderer is either Peter or John. If the witness was drunk, then it can be any. So it doesn't have to be a male. This is a multi-value mapping or a random set. So there's a probability distribution P here on the source space, as it's called, omega, which induces something more general than a probability. It's called a mass assignment. So it looks like a probability distribution, but it's on the power set of your domain of interest, your decision space, instead of the sample space itself. And this is induced by this, using this multi-value mapping, via this multi-value mapping. So what you get as a mathematical object in your decision space is something called the belief function. So a belief function, the belief value of an event is the probability of all the points in the source space such that their image implies the event A. And the plausibility of A is the probability of all the points in the source space whose image has non-empty intersection with the event of interest. These were originally termed by Dempster as lower and upper probabilities, because Dempster is a probabilist, is a believer in probability theory, and still is. He is alive. He's 96 or so. So in his view, the source of evidence is always a probability of some kind, but the way you reason with it depends on how linked is your decision space to the evidence, you know. And often this link is in the form of a multi-valued mapping or a random set. These lower and upper probabilities can be interpreted as lower and upper bounds to the values of an unknown underlying probability measure, but this is yet another interpretation which is disputed, and some people believe in this interpretation, some people reject this interpretation. There's a whole field called precise probability that Cassio probably won't tell you about, that reject this notion that lower and upper probabilities concern bounds on the true probability distribution. So these are belief functions. Belief functions are total probabilities induced by these mass assignments. So the belief value of an event is the sum of the masses of all the subsets of the event. So if you compare with this additivity in probability theory, the probability of an event is the sum of the probabilities of all the elements of the event. In belief theory, the belief of an event is the sum of the masses of all the subsets of the event. And that's because the subsets are assigned masses independently. There is no additivity here anymore. So every subset is assigned a mass independently, and to compute the belief value of A, you need to sum the masses up of all its subsets. This is quite a general, it's not the most general possible formalism, but it's quite general because it generalizes traditional crisp sets. So belief functions generalize standard sets, they generalize standard probabilities because probability distributions are special case of belief functions, at least in a finite case. You can represent complete ignorance by assigning mass 1 to the entire decision space or frame, as it's called. Instead of using a prior, you just say the mass of the whole thing is 1, and you don't have to specify what the masses of individual elements are. And also they generalize fuzzy sets or possibility measures, which are yet another model for uncertainty, although less general than this. So what are the semantics of belief function? And then I think I'll switch on to the other uncertainty theories for the last 15 minutes. But you will have the full slides, I think, on the website. So belief functions have multiple interpretations as set value random variables, like I discussed in the beginning with the clock die experiment. You can also see them as monotone capacities. So like I said, a capacity is a measure such that if A is included in B, then the measure of A is smaller than the measure of B. They're also a special type of credal set or convex set of probability distribution. So if you represent probabilities in a probability simplex, like for a sample space of 3 elements, X, Y, and Z, a belief function does correspond to a convex set of probability distribution. So, yeah, but it's a special kind of credal set. So there are more general credal sets that are not induced by a belief function. They also have an axiomatic definition that looks similar to that of probabilities. So the first 2 axioms are the same, but Additivity is replaced by this more general one called superadditivity, which looks very complicated, but it's just a combinatorial. It's just a function of the combinatorial properties of random sets, really. Okay, so I want to skip this bit and move on to the last part of the lecture. So just some other brief comments. So belief functions are not general creedal sets, like I said. So you can define complex sets of probabilities that are not belief functions. They're not parameterized families of distributions. So a parameterized family of distribution is a subset of all possible distributions, just like belief function, but they don't. All families of distribution do not correspond to belief function. For instance, you can define a family of Gaussian PDFs with zero mean and arbitrary variance. That's not a belief function. They're not confidence intervals either. Confidence intervals are one-dimensional, and their interpretation is entirely different. They're interval estimates. They're not epistemic models of belief. And they're not second-order distributions, although second-order probability distributions, so probability distributions on probability distributions are models of epistemic uncertainty, so they're acceptable models of epistemic uncertainty. An example of this, the most famous example is the Dirichlet distribution, which lives on a simplex. So you can see the Dirichlet distribution as a second-order distribution of probability distributions. So you can use second-order distributions to model epistemic uncertainty, but these are not belief functions. Although you can do, like, never ends really. The hierarchy never ends. Like I said, I wanted to skip to this final part just to give you a wider overview of the entire field and a fair representation, I think, of what's going on. So there are actually, I think I mentioned a few so far. There are different mathematical theories of uncertainty that compete to be adopted by practitioners. I think the general consensus is that there is no such thing as the best mathematical description of uncertainty, but this is subject to philosophical debate rather than anything else. Random sets, the ones that we've seen in a bit more detail, are not the most general framework, but as we argue here, they do naturally arise from set value observation, like missing data and scarce data. There are other approaches, and there also have been some attempts to come to a unified representation of uncertainty theory, which again have not led to full consensus. They're sort of a zoo, really, and they form sort of a hierarchy of encapsulated formalism from the least general to the most general. And here I try to represent that belief function random sets are infinitely monotone capacities, so which are less general than probability intervals, which are two monotone capacities. And then you have monotone capacity, general monotone capacity, which are even more general. Creedal sets. So belief functions are a form of creedal set, but creedal sets are not independent from monotone capacities, and so on and so forth. And there are less general formalisms as well. So I'm going to mention a few here. The most important one, I think Cassie is going to talk about it. Are you going to talk about this? Not so much. So I'll do this slide. And so in Wally's imprecise probability, which is a behavior approach to probability, you work with, at least initially, with lower probability, which are a function such that the lower probability of the union is not smaller than the sum of the lower probabilities of the two events. So you can see that belief functions are lower probabilities because because of superadditivity, they do satisfy this axiom. Then there are some criteria for which there are some reasons that due to behavioral probability that you want this lower probability to avoid sure loss. So to be the upper envelope of a set of probability measures, and you want it to be coherent. So you want the infimum of this upper envelope to coincide with the lower probability. When you do that, you get the convex set of probabilities, but not all convex set of probabilities can be described by focusing just on events. And this is what probably it's the focal point of all this book. You need to extend your sample space from events to gambles, so any real functions on the real line. In this interpretation, precise probability is equal to beliefs or inclinations to act. So like I said, they're like a form of behavioral probability. An agent believes in an outcome to the extent that he's willing to accept or bet on it. I'll skip this part. Yeah. Then there's monotone capacities. Like I said, I mentioned before, theory of capacity is another generalization of classical measure theory. And the axiom they have to satisfy is very simple, called monotonicity. We already talked about it. And any non-negative measurable function, f, on your sample space, you can compute the Choquet integral by doing this. Both the Choquet integral, monotone capacity, and natural extension of lower probabilities in the one interpretation generalize the Lebesgue integral. The order of capacity is the size of the sets for which the superadditivity constraint is holds, basically. So since this holds for any size of events, belief functions, and random sets are infinitely monotone capacities, but you can also define capacities for which superadditivity only holds for size of events up to a certain value k, and then these are called capacities of order k. In particular, you have capacities of order 2, and these are nice because they correspond to interval probabilities. So instead of defining a single probability for any event, you can define a lower probability and upper probability for that event. So you have an interval of possible probability values. And these probability intervals do correspond to capacities of order 2. That's what I was just saying. So you can have a set of probability intervals. This is one of the simplest possible measures of uncertainty. Instead of having a probability for each point of your sample space, you have a lower probability and upper probability. And these typically arise through measurement errors, measurements intrinsically of interval nature. And in engineering, there's a lot of use cases in which measurements are affected by errors or they're of interval nature. The set of probability intervals like this also determines a Credo set, which is a special class of all the possible Credo sets generated by lower and upper probabilities. And there are also special, and also every belief function induces a set of probability intervals. So a belief function is less general than a set of probability intervals. And that's what I said before, that an infinitely monotone capacity is less general than a two monotone capacity. There are fuzzy sets or possibility measures. These are due to fuzzy sets are due to Loptizade, as you know, but the rigorous mathematical description is called possibility theory. It's based on something called possibility measure, in which the measure of the union of events is just the soup of the measures of the individual events. This kind of measure is called the possibility measure, and it's uniquely characterized by a membership function on theta. So you have all the function of the membership values pi of x, and the measure of any event is just the soup of the membership values of its components. There's a good relationship between possibility measures and belief functions, in the sense that possibility measures are, again, a special case of belief function. Whenever a belief function is such that all its non-zero mass subsets are nested like this, you get a possibility measure. So possibility theory, possibility measures are a subset of all belief functions. I think I'm getting almost there. Another model worth mentioning is probability boxes, which is also used a lot in engineering. If you're familiar with cumulative distribution functions, as I think you are, probability box is just a set of a lower bound and an upper bound to the cumulative distribution function. So instead of having a lower bound and upper bound to probabilities of events, you have a lower bound and upper bound to the cumulative distribution function of a random variable. So this is represented, this is represented here by this picture. This is the lower CDF and this is the upper CDF. So a P box is the set of all possible CDFs comprised between the lower one and the upper one. Again, this is used a lot in engineering and for reasons due to the type of data that they work with. Okay, so I think I'm almost done, and I hope I expressed what I wanted to express. So the purpose of the tutorial was to argue that classical mathematical probability is not adequate to model epistemic uncertainty associated with scarce data, rare events, propositional data, uncertain data, and missing data, and so on and so forth. There are more general ways. I mean, both the Bayesian and the frequentist interpretation are flawed in my mind because they don't hold up to scrutiny in some respect. There are more general ways of modeling uncertainty, and we talked about random sets. We also talked about a number of other measures of uncertainty, like probability intervals, Creedal sets, monotone capacities, lower number probabilities, and most of them are encapsulated in a sense that one is less general than the other. And okay, it's not in this slide, but I think what I like about this is a more general mathematics. I mean, they're more complicated. So if you actually have time, you want to spend a little bit of time on understanding the detail of these things. They are a bit counterintuitive and they are mathematically more complicated than standard probability, but they do have properties that are philosophically nicer than classical probability, and also suit better the use cases that we normally have in AI and machine learning. Because AI, machine learning is a giant scarce data problem. You want to learn a mapping from data points to input spaces to output spaces from a very limited amount of data. And this has consequences. And if you don't realize that, I mean, the whole model adaptation problem in AI, machine learning, is a problem of dealing with scarce data. So epistemic uncertainty is intrinsic to machine learning. This is what we try to argue with this project, with the epistemic AI project. This is what we're working on. And you will never solve, you will never address from a fundamental point of view the problem with model adaptation in machine learning if you don't acknowledge that this is due to uncertainty induced by scarce data, or data not of good enough quality, or data that doesn't cover the entirety of your sample space, and so on and so forth. Okay, I think I'm done. So if you have any questions, feel free to ask.
Thank you very much. So, first, I would like to what is that? They quality. So why not each and explorations have gotten the done we are doing things way and
In what you there being with that noise, learning without the your voice. Eventually, hopefully, you That's the way you get it. It's not doing machinery. Learning something which you learn from data, you learn data associated, derived from data, when there is a domain of something. That doesn't quite solve it now. Strong in the judgments, but yet set the data stories. So any application could be like abuse but in AI and in your awareness of just the dynamics so your data is so if you are in so the stages so helps with the spectrum and everything create exchange self with the data situations. Any that doesn't change. Rather, the legend said he would estimate certain yes, romantic learns not to learn says we would be able to meet data and we which costs money. It's a money. So in learning is expenses. We need to select, be selective about where you have data. Because having one is on the yes, what's yes, what the others really never anything companies. So that first so that's it. Usually, then in the case, at least a lot of the sense. So if we use robotic education, so the method that is really used to restore
some sites and then see and the students is
Yeah. I just- Is chat, you know, that the general information, but within the community and they big data, they have that they can within the community. And so yeah, even
some of the which life already life is you learn one of these things that especially really to learn you don't handle it's going to be less biased than anything. And also we can have bias on the public story. It could also be a bit scenarios so like we can understand. One test and my hypothesis that when you understand is more conscious about statements, the like standing on the in the idea which will be so where's the control of data? I mean, it's I don't know, next week as it's still data. No, should I ask for permission? Yesterday, they did so by several writers because I didn't want to just steps from their voice. It's not a technical problem. It shouldn't be stopped on crawling people. So if to start with, anybody was interested. Well, and then again. Then we found that as a case, we did the kind of brother or before then we don't have everything in our space. Wrong. What are you saying? You can do things, you can select data and metadata to do it. You need a model to tell you what is the effect of what you do. I have a
That's fine. Let me just put this.
Yeah,
one.
we have talked, you have talked about a lot of different methods of express, about different methods to do it, which was great, and thank you, and I never heard of it.
But so all of these many of the methods, we lack the fact that in the domain, the domain